All right, so let's look at arc length of vector-valued functions. So I have a vector-valued function with components x, y, and z on the interval from a to b. I'm thinking of vector-valued functions as tracing a curve in 3D space. T can be interpreted as time. So from time a to time b, the arc length of the vector-valued function gives you how far the object has moved, how far the particle has traveled along the curve between these two times. Now we've already seen arc length for parametric equations is this form. If you think about it for a second, this is only the magnitude of the derivative of your vector-valued function. So there's a especially nice form for the arc length of a vector-valued function. Let's do an example. The arc length of the helix r of t is 2 cosine t, 2 sine t, let's say t, that's a vector-valued function, between the curve, the values on the helix given by 2, 0, 0 and 2, 0, 2 pi is the integral. Now, where does my integral begin and where does it end? Which values of t give me these 2 points on the helix? Well, I could see looking at the third component that the starting value of t is 0 and the ending value of t is 2 pi. So I'm going to integrate from 0 to pi the magnitude of the derivative of my vector-valued function. So the derivative of this vector-valued function is negative 2 sine t, 2 cosine t, and 1. Now, the magnitude is the integral from 0 to 2 pi, the square root of negative 2 sine t squared, that I think will give me 4 sine squared t, plus this middle component squared, 4 cosine squared t, plus 1 squared. And I integrate with respect to t. Now, sine squared plus cosine squared is equal to 1. So 4 sine squared plus 4 cosine squared is equal to 4. This is really just the integral from 0 to 2 pi of the square root of 5. So you can integrate and you'll get the arc length, which is the square root of 5 times 2 pi. That's actually the length of one rotation of this helix. Okay, so I'm going to motivate the next topic by asking this question. What is the difference between the following vector-valued functions? So here's the first vector-valued function, r1. I'm going to say r1 is equal to just a circle, cosine t sine t. I'm going to let r2 be my second vector-valued function given by cosine 2t sine 2t, and my last vector-valued function, r3, will be cosine t cubed sine t cubed. In all of these vector-valued functions, I'm going to let t be any real number. So the difference between these vector-valued functions is not the shape of the underlying curve. The underlying curve in all three of these examples is exactly the same. It's a circle of radius 1. The only difference between these vector-valued functions is how fast I trace out the circle. So the first vector valued function traces out a circle of radius 1. So let's say here's my circle of radius 1. At t equals 0 for the first vector valued function, I'm at this coordinate. And then as t ranges, so there's my t equals 0 for r1. Then here for r1, halfway around the circle is when t is equal to pi. However, the second vector valued function traces the same circle just twice as fast. Twice as fast. It takes me, for r1, this is t equals pi right here, this point. But that's the value of t equals pi over 2 for r2. So r1 traces out the circle, r2 traces out the circle faster, twice as fast. And the third vector valued function traces out the same circle, but the speed is changing. Here I'm at t equals 0, but as I go around this circle, as I travel around this circle, the value of the speed increases. So here I'll try to move my pencil according to how these vector valued functions trace out the curve. So the first curve is traced out with a nice even pace. The second curve, twice as fast. And the third curve starts out slow, because t cubed starts out slow. The graph of t cubed looks like this. So at t equals 0, I go slow and then I speed up. So the third curve, I go slow. And as I get further, I get faster and faster. Okay. All of these parameterize the same curve. So the same curve is traced, but at different speeds. These are known as 3 different parameterizations of the circle. They all parameterize the same circle. But here's what I'd like to do. I'd like to find a parameterization such that the arc length from t equals a to t equals b is exactly b minus a. So here's a picture of what I'm looking for. So I have a vector valued function. Let me draw one in R2, since R2 is easier for me to draw than R3. So I have a vector valued function. There I go. There's my vector valued function r of t. Here on the curve, I'm at the value t equals a. And here, at another point on the curve, I'm at the value t equals b. I want just the right parameterization such that the length of the curve on the interval from a to b is exactly b minus a. So if I take a to be 0, the distance traveled after 1 second is exactly 1 meter. The distance traveled after 2 seconds is exactly 2 meters. The distance traveled after 3 seconds is exactly 3 meters, and so on. I'm going to want to trace out the curve at the perfectly even pace to trace out a meters after a seconds. So the method to do this, I will outline for you now. Here's a how-to guide on how to parameterize by arc length. How to parameterize by arc length. So I'm going to give you a step-by-step guide on what to do. So step 1, find this function I'll call s, which is the integral from 0 to t of r prime of u du. This is the arc length of the vector valued function r on the interval from 0 to t. Okay. Step 2. Find the inverse function s prime of t. So this is the inverse function, not division. It's not 1 over s. It's the inverse function. I'll do an example in a second, but the third step is the correct parameterization is the vector valued function that you started with, except instead of plugging in t, I plug in this inverse function, s inverse of t. Okay, let's finish this video with an example of parameterizing by arc length, following this procedure. Okay, so consider, what about the vector valued function r of t? Here, why don't we do a helix again? That's a nice classic example. So let's do the helix cosine t, sine t, t. I'd like to find the parameterization, so if I travel t units in time, I've traveled a distance of t along the curve. So step 1, the first thing I'm going to do is let s of t be the integral from 0 to t, the derivative of this vector valued function, except I'm going to plug in u wherever I see a t. The dummy variable in the integration is u. So I will get negative sine t, cosine t, 1. This is very similar to the example we started this video with. It's the integral from 0 to t. Oh, these should have been u's, huh? U's, my dummy variable. So I get the square root of sine squared u plus cosine squared u plus 1. That's the square root of 2. The answer, square root of 2t. So that is the function s. The inverse function, s inverse of t, is the function that undoes multiplication by the square root of 2. So the function s takes your number t and multiplies by the square root of 2. The inverse function undoes that operation. So the way to undo multiplying by square root of 2 is to divide by the square root of 2. Notice, these are inverse functions because when I put one function inside of the other, I get, so if I plug in 1 over the square root of 2t for the inverse function, then s of this is the square root of 2 times 1 over the square root of 2t, which gives me back just t. And we know that's a defining property of inverse functions. When you compose the two functions, you should get back t. All right, so finishing up, my parameterization is the original function, except I'm going to put in 1 over the square root of 2t wherever I see a t. So this would be cosine 1 over the square root of 2t sine 1 over the square root of 2t and 1 over the square root of 2t. So if I travel t units, if I travel t seconds along this curve, then I've actually traveled a distance of t units. Okay, wonderful. See me for the next video.